Today's lesson is on something called L'Hopital's rule. So I'm going to write it out here for you, and then we'll talk about how do we use it. So L'Hopital's rule says, if f of x over g of x is 0 over 0 or infinity over infinity, and these have a name. This is called the indeterminate form. Okay, so if it's 0 over 0 or infinity over infinity, then the limit as x goes to c is of f over g is the limit of the derivatives. So if we get 0 over 0 for a limit, then we can take the derivative of the top function and the derivative of the bottom function and evaluate the limit there. So let's look at an example. So this limit, the limit as x goes to 2 of x squared minus 4 over x minus 2. You've been doing these ones since pre-calculus. And how we did this in pre-calculus and at the beginning of the semester is to factor. So this factors to x plus 2, x minus 2, which allows me to reduce the x minus 2's. So this is the limit as x goes to 2 of just the x plus 2. Then we evaluate the limit, so we get 2 plus 2, which is 4. Now let's do the same thing with L'Hopital's rule, and we can apply it because if I plug in 2, I get a 0 on the top and a 0 on the bottom. So let's copy the problem down. So L'Hopital's rule says that this limit is equal to the limit of the derivatives. Now you're not using the quotient rule or anything here. You're simply just taking the derivative of the top, which would be 2x, over the derivative of the bottom, which would be 1. Well, this simplifies to just 2x, and I evaluate that limit by plugging in 2. So this is going to be 2 times 2, which is 4, which is good news because that's what we already established. This next one is the same equation, but rather than going to 2, we're going to negative 2. So if I plug negative 2 in, I'll get a 0 on the top, but I am not going to get 0 on the bottom. So this is not 0 over 0. So I cannot use L'Hopital's rule, but that's okay. I don't need to, because this is just going to be negative 2 squared minus 4 over negative 2 minus 2, which would be 0 over negative 4, which is just 0. So you always have to check for 0 over 0 to find the limit. All right, next one. As we go to 0, sine is going to go to 0, and 0 is going to go to 0. So we can use L'Hopital's rule. So this is going to be the limit as x goes to 0. The derivative of sine is cosine of x. Derivative of x is 1. So this is just going to be the cosine of 0, which is 1. And this was one of the limits at the beginning of the semester we discovered graphically is 1. Next one here, if I plug in 0, cosine is 1, so we're going to get 0 over 0. So we can use L'Hopital's rule. Derivative of this top here, derivative of 1 is 0, derivative of cosine is negative sine, so this is going to be just a positive sine x over 1. So that's going to be sine of 0, which is 0. All right, this next one, if I plug in 0, we're going to have sine of 0 over sine of 0, which is 0 over 0. So now I'm going to take the derivative. So this is going to be 5 cosine 5x over 4 cosine 4x. Evaluated at 0, cosine of 0 is going to be 1. So this is going to be 1, this is going to be 1, so this is just going to be 5 over 4. All right, in this next one, same, if I plug in 0, I'm going to have 1 minus 1 over 0. So this is 0 over 0. So this is going to be the limit as x goes to 0 of derivative here is still going to be sine of x over 2x. If I plug in 0, we're going to get 0 over 0, which means we need to do the derivatives again. We still can apply L'Hopital's rule because it's still 0 over 0. We get cosine x over 2. Now if we plug in 0, we're going to have the cosine of 0 over 2, which is 1 over 2. Okay, here if I plug in 0, we get 0 over 0. So we're going to have the limit as theta goes to 0 from the positive side of sine theta over, we're going to have to use the chain rule here on the bottom. So the outside function is the squared. So we're going to have 4 sine of theta times the derivative of sine of theta, which is cosine of theta. Now if I try to plug in 0 here, it's still going to be 0 over 0. So you could use L'Hopital's rule again, or algebra. Okay, the sine over the sines reduce. So this is the same as the limit as theta goes to 0 from the positive side of 1 over 4 cosine theta. Plug in 0 here, cosine of 0 is 1, so this is going to be 1/4. Alright, so let's look at this problem here. So we have the limit as x goes to 0, 1 minus cosine x plus x squared. So the derivative of that is sine over 1 plus 2x. The derivative of that is cosine over 2, which would be 1/2. But if we were to graph this, so in my y equals, I've got 1 minus cosine x over x plus x squared. If I go to the graph, at 0, that's not approaching 1/2. That appears to be right at 0. So what went wrong? Well, the key is we have to check for the 0 over 0. So here we have 0 over 0. Here we have 0 over 1, because if I plug 0 in here, I still have this 1. So this I can't, that's no longer valid because this is not 0 over 0. But we can evaluate that limit there. So this limit is going to be 0 over 1, which is 0, and that's what we saw on the graph. Okay, hopefully you understand this is the definition of a derivative. But we're still going to use L'Hopital's rule. So if I plug in 0 for h, we have sine of x minus sine of x, which is 0 over 0. So this is the indeterminate form. So I'm going to take this derivative and I'm going to take it with respect to h because that's my variable. So what this is going to leave me with, on the top, the derivative of this is going to be cosine of x plus h times the derivative of h, which is just 1. The sine x is actually going to go away because it doesn't contain an h, over 1. So this is now the limit as h goes to 0 of cosine of x plus h, which I can plug in 0, gives me cosine of x plus 0, which is cosine of x, which is the definition of the derivative. Here, also the definition, the alternate definition of a derivative. If I plug in pi, we'd have cosine pi minus cosine pi over pi minus pi, so that's 0 over 0. So we'll take this derivative. So derivative of cosine, negative sine x, that's going to be a constant over 1. We plug in pi, so this will be negative sine of pi. Sine of pi is 0, so this is 0. And again, that would be the derivative of cosine evaluated at pi, which is what we did. The next form we're going to look at is infinity over infinity. So if I look at this, as we're going to infinity, x is going to go to infinity, and e to the x is going to go to the infinity. So this is the second situation where we can apply L'Hopital's rule. So I'm going to take the derivative, so we're going to have 1 over derivative of e to the x is e to the x. So now as we go to infinity, this is going to get bigger and bigger and bigger, so we're going to have 1 over infinity, which is going to be 0. Okay, what about x cubed? So we still have infinity over infinity, so we can take the derivative, so this will be 3x squared over e to the x. Well, that's still infinity over infinity. So we'll do L'Hopital's again. So we'll have 6x over e to the x, which is still going to be infinity over infinity. So we're going to have to do this one more time. So we have 6 over e to the x. Now we can evaluate the limit. So this is going to be 6 over infinity, which again is going to go to 0. So if you look at this last case here, x to the n over e to the x. So x went to 0, x cubed went to 0. And what's going to happen is as I keep taking derivatives, no matter what that power is, eventually it's going to go to a constant. So this is always going to be 0. And the general case here is that the exponential function grows faster than a polynomial. Just in general. So we can look at the limit that way, that if I have a polynomial over e to the x, this is always going to grow faster eventually as we go to infinity than the top is going to go to. All right, as we go to infinity of natural log of x over e to the x. So that's going to be infinity over infinity. So natural log's derivative is 1 over x over e to the x. So I can rewrite this as 1 over x e to the x. Well, this denominator is again going to grow bigger and bigger and bigger, so this is going to be 0. So the same relative growth. Logs are going to grow way slower than exponentials. So e to the x grows faster than that natural log function. Okay, let's look at log compared to x. This is still infinity over infinity. So we're going to have 1 over x over 1, which is just 1 over x. As we go to infinity, this again is going to go to 0. So this again is growing slower than x. You wouldn't maybe think that x is, because x doesn't grow particularly fast, but it does grow faster than logs. X grows faster than natural log of x. So we're going to summarize this on the next page. So just in general, logarithms are going to grow the slowest. Polynomials will grow faster than logarithms. And then exponentials are going to grow the fastest. Okay, let's look at one more infinity over infinity. So both of these are going to go to infinity, right? And if you look at this limit as you go to infinity, hopefully you know already what the answer is, but we're going to arrive at that same conclusion using L'Hopital. So we'll take the derivative of the top over the derivative of the bottom. Still infinity over infinity. So we'll have 6x over 24x, which is going to reduce. So the x's will reduce, and then 6 over 24 reduces to 1/4. So the limit as x goes to infinity of 1/4 is 1/4. And I said in the beginning, you should already know this limit because we're going to infinity. The degree is the same, so it's the ratio of the leading coefficients. But we arrived at that same conclusion using L'Hopital's rule. Okay, there are other indeterminate forms besides 0 over 0 and infinity over infinity. So these include 0 times infinity. It includes infinity minus infinity. It includes 0 to the 0, 1 to the 0, and infinity to the 0. These are not cases that will be on the AP test. So we'll do just a couple quick examples to show you how you would handle them. The way we are going to handle them is if you have one of these forms, we're going to use some algebraic stuff to get either 0 over 0 or infinity over infinity, because then we can use L'Hopital's rule. So if we take a look at this first one here, as we go to infinity of x times 1 over sine of x. As we go to infinity, this is going to go to infinity. This is going to go, 1 over x is going to go to 0, and sine of 0 is 0. So what we have here is infinity times 0. But I can rearrange this to make it so that it's 0 over 0. So what we're going to do is we're going to rewrite this as sine of 1 over x over 1 over x. Okay, I rewrite this x as the reciprocal of itself. This would simplify to this, but this now is 0 over 0, which allows me to use L'Hopital's rule. Derivative of sine of 1 over x is going to be cosine 1 over x times the derivative of 1 over x, which is negative 1 over x squared. Derivative of 1 over x is still negative 1 over x squared. So those negative 1 over x squareds cancel. So all we have here is the limit as x goes to infinity of cosine 1 over x. 1 over x as we go to infinity is going to go to 0. So this is going to be cosine of 0, which is 1. Okay, this next one, as we go to pi over 4, tangent at pi over 4 is 1, so this is going to be 0. Secant of 2x, so that would be secant of pi over 2. Well, cosine at pi over 2 is 0. So secant is actually at an asymptote there. So this is again going to be 0 times infinity. But I'm going to rewrite this one using the fact that secant is really just 1 over cosine. So this is going to equal the limit as x goes to pi over 4 of 1 minus tangent of x over cosine 2x. So I haven't changed anything, I just reorganized it. Now as we go to pi over 4, like I said, this is going to go to 0. Cosine of pi over 2 is 0, and that's still going to be 0, but it should be a minus. So let's take the derivative. So derivative of 1 is 0, derivative of tangent is secant squared. So it's going to be negative secant squared x over negative 2 sine 2x. Okay, now we can plug in pi over 4. So the negatives are going to go away. We're going to have secant squared pi over 4 over 2 sine pi over 2. Okay. Well, cosine of pi over 4 is root 2 over 2. The reciprocal of that is just root 2. So this is going to be root 2 squared over sine of pi over 2 is 1, so this is going to be 2. So we'll have 2 over 2, which is 1. Okay, this next one, as we go to infinity, this is going to be 1 to the infinity. This one, we have an exponent in the base, or we have an exponent, a variable in both the base and in the exponent. So what we're going to do is look at this without the limit for a second. Okay, we have a trick of using logs to be able to bring exponents out front. Okay, so we're going to come back. I'm going to look at this side of the equation, and I'm going to look at this limit. So I'm going to investigate the limit as x goes to infinity of x times natural log of 1 plus 1 over x. Well, x is going to go to infinity, and natural log is going to go to, natural log of 1 is 0. So this is going to be infinity times 0. I'm going to rewrite this again using a reciprocal. So we'll keep the natural log of 1 plus 1 over x. And then in the denominator, instead of x, I'm going to have 1 over x. All right, so then we're going to take the derivative of the top and the bottom, because now I have 0 over 0. So derivative of natural log is 1 over x. So this is going to be 1 over 1 plus 1 over x times the derivative of the inside, which is going to be negative 1 over x squared, all over the derivative of 1 over x, which is negative 1 over x squared. So those can cancel. So 1 over 1 plus 1 over x. This is going to go to 0, so this is going to be 1 over 1 plus 0, which is 1 again. So that's what this goes to. So we're going to say that the natural log of y is going to go to, this goes to 0. So then y is going to go to, this goes to 1. So if I raise both sides to the e, so e to the natural log of y is going to equal e to the 1. That means y is going to be e, which means this limit is really e. And this is just one you're going to have to memorize. That the limit as x goes to infinity of 1 plus 1 over x to the x is e. Last, we have a part of a free response problem. So this is on the 2016 AP test. It says, consider the differential equation dy dx equals x squared minus 1/2 y. It says, let g of x be the particular solution, we'll learn what that is eventually, to the given differential equation with g of negative 1 is 2. And we want to find the limit as x goes to negative of g of x minus 2 over 3 times x plus 1 squared. Well, okay, if g of x at negative 1 is 2, then we have 2 minus 2 on the top, and x is negative 1, so this is 0. So this is L'Hopital's rule. On the AP test, according to Mrs. Thurkel, if this year when they graded it, if you didn't state that this was 0 over 0, you didn't get the credit for the question. So you have to show that it's 0 over 0, so you know you can use L'Hopital's rule. So we're going to take the derivative. So just straight the derivative of the top over the derivative of the bottom. The derivative of the top is just going to be g prime of x. The derivative of the bottom is going to be 6 times x plus 1. Well, I can tell right away that the denominator is still going to be 0, but what about the numerator? Because we need it to be 0 over 0 to use L'Hopital's rule. Well, g prime of x is just a different way of saying dy dx. So what we need to investigate is dy dx, this x squared minus 1/2 y, what's happening at -1? So I'm going to plug in -1 for x and 2 for y. So this is going to be 1 minus 1, which is 0. So this is 0 over 0. We can use L'Hopital's rule again. Now we have, goes to -1, g double prime of x over 6. This is not going to be 0 over 0, so now we need to find the value of the second derivative at the point -1, 2. So what we need to do is take this derivative again. So the second derivative is the derivative of that. So this is going to be 2x minus 1/2 dy dx. I'm evaluating this at the point -1, 2. So this is going to be 2 times -1 minus 1/2. We already know what dy dx is at that spot. It's 0. Or you can plug it in again, but you're still going to get 0. So this second derivative is -2. So this is going to be -2 over 6, which you can leave it just like that, or -1/3. So that's kind of an interesting example, an interesting execution of L'Hopital's rule and differential equations.